Welcome to EDU World Space.
I'm going to look at problems 114 and 115 together because they both analyze this structure or this system where we have um, power transmission cables suspended between these towers here. We are told that these ones are 300 feet apart and these are 200 feet apart, and that the sag here is 10 feet. We are not given the sag for this one in problem 114, but we are given it in problem 115 and asked to find some other value. So we're told that the cable in both problems weighs 10 pounds per foot. So we have W naught equals 10 pounds per foot. We can just go look from the book, write down what our the function for our the shape of this curve is. And again, we're going to have a different shape for here and for here. So I'm going to call this this one a y1 as a function of x1, and this one y2 as a function of x2. And again, these are at the minimum, which is in the center because these supports are at the same height. And so then we have the function for this side over here. We can then use plug in the value that at this point here at xb1, which is 150 feet, y1 should be h1, which is 10 feet, and that tells us that we have the horizontal tension in here is, basically we need to use a root finding algorithm or a trial and error to find what this value is. We can't just invert this equation. But we get the value here from trial and error or from plotting it and finding the root, and it is 11.3 kip. Now in this problem, we want the net horizontal force on this support structure to be 0, so that this cable is pulling on it the same amount as this one is, but in opposite directions. So we don't have this thing kind of acting to being bent. It's just supporting the weight. So what we can do is then we can simply put this value. We want this value to be the same as this, so we put it into here, and that will allow us, and put it into here, and that will allow us, if we plug in this distance here, which is 100 feet, we find that the sag is 4.44 feet. So that would be what we'd need a sag in this span. In this span, we have 10 feet. So this one would have to sag a little less than half as much as this one, even though the length is not half. So in the problem 115, we're actually given what this is, and we're told that this is also now 10 feet. The height here is now 10 feet. And this problem we want to determine the resultant vertical force on the cables exerted on this tower here. So now we're not going to have them equal and opposite here. So we can do all that. We can plug in. Well, we still get this value here. Okay, there's nothing changed with that. But now if we plug in that h2 is 10. And so we plug in y2 at 100 feet needs to be h2. We can find fh2 here, again numerically, and we'll find that that is 5.02 kip. And subtracting these two, we get a net force on this of 6.25 kip. So in that case, we are pulling this thing this way. Now we have, let's see here. Yeah, we're pulling this one is pulling this way. I think actually we're pulling it this way because F1H is this value, and then this value So we're pulling the cable. Yeah, we're pulling the cable this way, so the tension on the structure here is actually the opposite in this direction. Now we are also asked we're asked to determine the vertical force also, which means we need to figure out what the length is because we know the mass per unit, the weight per unit length. So if we know the length, we can get the total weight, and we know that each one of these, because of symmetry, each pillar here carries half of the weight. So we can figure that out using the equation that we can write for S as a function of X. And then S as a S at so if we have S1, so we have S1 as X1, and so L would be S1 at XB1, which is 150 feet, and then we need to double that. So we have find this length, and then the other half gives us the total length, and that turns out to be 301 feet. So about an extra foot of over, which is kind of interesting because this thing sags 10 feet, which seems a lot, but the the cable is actually only 1 foot longer than the distance between these towers. Now in this case we can do the same thing, and we'll find that the cable is 201 feet. And again, it sags 10 feet. Again, these are there's more decimal places here, but I rounded them to 3 significant digits. So now we have 502 feet of cable that weighs this much, and we take half of it because only the weight of this section and this section are carried by this, and that turns out to be minus 2,510 pounds. So if this was in the positive direction, so again we're pressing down on this cable, on this if we look at the value for this support, it's compressing it. So that's why you need to make sure that these things are pretty sturdy so they don't buckle.